All right, today's lecture is to finish off voltaic cells, and that's something called what happens to the voltage of a cell as a cell operates, and what happens with the voltage cell when we have varying concentrations of reactants or products. This is something called the Nernst equation, which is the mathematical way we can actually calculate it. I'll show you a couple examples of that, but more importantly, the concept in this is going to be just effectively being able to describe what would happen to the voltage of the cell. Would it increase or decrease upon changing concentrations? Now, what I've written up here is a standard cell where we happen to have a piece of where we have the zinc half reaction and the copper half reaction written in the states which it would create a voltaic combination. And if you go through and find the two cell voltages, you would end up getting a cell voltage like the previous homework. The cell voltage would be 1.10 volts. This would be the case when both the concentration of the zinc is 1 molar and the concentration of the copper is 1 molar. Now, if we vary the concentration of either of those two substances, the voltage of the cell will no longer be 1.10 volts. And this comes into play with looking at when they're each 1 molar, we are operating with a K value. When we change that from 1 molar concentration, we're no longer operating a K but a Q. And if you remember how we calculate K and Q, it's concentration of products over concentration of reactants. So, as a cell operates, okay, the voltage will increase. Well, the voltage will increase when the reaction is even more spontaneous, or the reaction is even more favoring product formation. What would cause a shift in even more products to form than at the standard concentration of K? What would cause it to want to shift more to the right? And two things. If I would increase the concentration of the copper, or if I would decrease the concentration of the zinc, I would have a greater differential in potentials, and that would cause the cell to be even more spontaneous and to favor even more product formation. So whenever we increase the concentration of a reactant or decrease the concentration of product, your voltage will end up being greater than the 1.10 volts, where we have them both being at 1 molar concentrations. Okay, so this is where we'd set up the cell where we'd have even a greater differential in concentration values. Okay, now again, I'm not talking at all about the zinc or the copper. That's because these are solids, and if you remember back in equilibrium, whenever you have a solid or liquid state material, they are not involved in either Q or K equilibrium expressions. Now, as a cell, let's say we set up the standard cell and we hook up the voltage and the cell reads 1.10 volts. As the cell operates, what happens as the reaction operates? Well, we'll notice that the reactants, as the cell operates and goes spontaneously to form products, you'll notice that the concentration of the reactants begin to decrease over time as the cell operates, and the product concentration, in this case the zinc, will increase over time. So as the cell operates and these concentrations begin to change, the voltage of the cell will begin to drop, and that will cause a decrease. So my voltmeter, as the cell continues to operate, will get less and less. And this is typical for most batteries. You can look at it your cell phones. As you operate them and don't have them plugged in, you'll notice that the percentage of the cell battery will begin to drop over time. And that's because the higher potential flows into lower potential, and eventually as this one lowers and this one increases, eventually they get close to being at the same electrical potential, and when that happens, the cell stops operating. So the concentration of reactants decrease over time, the products increase, so the voltage drops, and it keeps dropping until the cell voltage reaches 0. When the cell voltage reaches 0, the differential in potential is exactly the same. Okay? So how do we calculate that voltage of the cell as the cell operates? And that's where we end up getting the Nernst equation. As these concentrations change, what happens to it? And the mathematical equation, which is the one that we're going to use, or I'm going to use most often, is going to be this one. E is the voltage of the non-standard cell. So after a period of time and the cell has operated for so long and its concentration of the reactants have gone down, products gone up, what did the voltage be after a certain period of time? E naught is what the voltage should be at the beginning if it's a brand new battery or a 1 molar concentration on both sides of the reaction. So the Nernst equation is mathematically a way for us to be able to calculate the voltage at any time, knowing the concentrations of the substances. So let's say after the cell operates for a while, let's say the copper drops from 1 molar, let's say it's cut in half. And because the copper goes down, the zinc will increase. Okay, and since it's a 1-to-1 ratio, if the copper goes down by 0.5, the zinc will go up by 0.5. And so the copper concentration will be 0.5 and the zinc concentration at that moment in time will be 1.5. Let's use the Nernst equation and figure out what that voltage will now be. So the new voltage will equal to the original voltage. Well, the original voltage of the cell is 1.10 volts minus the product of 0.0592 volts times the log of Q. And again, the log of Q up here is going to be the concentration of products over reactants. So the products is the zinc, which ends up being 1.50 molar, and the concentration of the copper is the only reactant that we have because the other two states of zinc and copper are solid states, so they're not involved in Q, and that will then be divided by N, which is the number of moles of electrons transferred. And we'll see here that both the zinc and copper change their oxidation state by 2, so there's 2 moles of electrons. So now if we go ahead and punch that in and take the log of 1.5 divided by 0.5, or in essence the log of 3 times 0.0592 times 2, we end up getting, and then subtracting from 1, we get a non-standard voltage now of 1.086 volts. Okay, so the product of this up here was 0.014 volts. Okay, and so we can see there that as the cell operates, that voltage will decrease over time and the voltage will drop. So this is the Nernst equation. Okay, so down below, here's another example of this. It said explain what will happen to the following cell volt potential if the concentration of the iron 3 was changed from 1 molar to 0.1 molar. Okay, so here we've got the iron 3 is going to go from 1 molar down to 0.01 molar. Oops, excuse me, 0.1 molar. What's going to happen to the voltage? Well, in the national exam, if you were to take it with concentrations, they no longer would ask you to calculate what that voltage is. Instead, they ask you to predict. Well, you'll notice that the concentration of the reactants went down. So because the concentration of the reactant went down, this would cause then the Q value, if you look up here, since the reactant goes on the bottom, when we take the value of that, the log of that, and take the log of that, we're going to get a value, or I should say, the log of Q is going to be a number that is going to be greater than 1, and therefore that is going to cause the voltage then to decrease or to drop. So because the Q value, when the Q value is 1, we'd get a value of 0 because the log of 1 is 0. But here, because the reactant's on the bottom, we're going to take the log of a number that ends up being bigger than 1. When that is the case, the voltage ends up being dropping. So we had predicted to be less. And Le Chatelier also predicts the same thing. When we decrease a reactant concentration, the reaction would be not as favorable to the right. It's going to shift more to the left to produce more of the removed reactant, and that's going to cause a voltage to drop. Now, using the new equation, the Nernst equation, we can actually figure out what that voltage is going to be. 0.0592 times the log of, okay, so we're going to assume the other concentrations are 1. So on top, the products are all going to be 1 times 1 squared, so that's all going to be 1. All over the concentration now is going to be 0.1, and you'll notice because there's a 2 in front of it, we'll square it. All over the value of 2 electrons being transferred. Okay, so if we go ahead and punch this out, And I hadn't done that before. Alright, so the log of 1 divided by 0.1 squared, it's being 2, when the 2's cancel, and so we're going to end up having this whole term is going to end up becoming 0.0592 volts, so 0.91 minus 0.0592, and we get a new voltage of 0.85 volts. So we predicted that the voltage would drop, and indeed that's exactly what we see. Okay. One last thing I want to talk about when it comes to these changes in concentrations in the Nernst equation. We can actually create something which is called a concentration cell. A concentration cell is where we actually have the same exact half reaction, or same reaction on both sides. In this case, we have both zinc mixed with the zinc, but the only difference between them is on one side we have a molar concentration of 1 molar zinc. On the other side, we have a different concentration, in this case 0.001 molar. If I vary the concentration of the substances, believe it or not, I end up getting voltage. And we find out is the concentration, the side that has the lower concentration, it's going to want to increase its concentration, and the higher concentration side is going to want to decrease. And therefore, on the lower side, the zinc substance is going to want to be produced, and therefore the lower side of the reaction will have the electrode, the zinc electrode will actually flow into the solution, increasing the ions. And therefore what that means is that the side that has the lower concentration will effectively react or act as the anode. The higher concentration side will react as the cathode. And if you remember back to our introductory use on cell potentials and voltages, is the electrical current will always flow from anode to cathode. So I know the electrons are going to flow from the lower concentration to the higher concentration in order to get the two concentrations on both sides of the salt bridge to being effectively the same. And we've created what's called a concentration cell. Okay, what would the concentration of this voltage be? Well, first of all, if I were to add these two voltages together, these two half reactions, they end up canceling out to 0. If I sum up the voltages of the anode and the cathode, it all sums the voltage to 0. Because if they were both 1 molar on both sides, there would be no voltage because there's no difference in concentration. So, using the Nernst equation, okay, the standard voltage would be 0 because they would both have a voltage of either 0.76 volts or negative 0.76 volts. So the only voltage we're going to get is from the difference in concentrations. 0.592 times the log of Q. Now, for the log of Q, we need products over reactants. In this case, the Nernst equation is N, my fault originally. In this case, we're transferring 2 electrons, so it's being 2. All right, now we have to figure out who's the reactants, who the products would be. Well, because the anode, okay, is going to be producing zinc ions are going to be produced on the anode side and the cathode side, we're going to end up having 0.001 over 1. Okay? Because the electron current flows from the anode to cathode, we'll notice that the zinc on this side is behaving as the reactant because it's being consumed, and on the other side, the zinc is acting as a product because it's being produced. So the 0.001 molar will go on top because it's the product over the reactant of 1 molar. So now if I go ahead and take the log of 0.001, times that by 0.0592, divided by 2, and take the negative of that answer, I get a voltage of this cell to be 0.089 volts, or 89 millivolts. So we can actually get voltage by creating combinations of the same substances but just in varying concentration. These are called concentration cells. There's some practical applications of this, one of them being an actual pH meter, a pH electrode. When we've done pH titration curves earlier in the year, the electrode itself is an example of a concentration cell, and there are practical applications used in a lot of different varying applications. Okay, so I just wanted to show you how this can also be applied in another type of scenario. All right, so that'll conclude today on the Nernst equation, how to effectively use the equation. There is no homework with it. It's just a concept I wanted to review with you and show you. And again, my main focus right now is to complete the material that typically would have been on the national exam, just to finish off the year. Tomorrow, we're going to go through electrolytic cells, and then you'll have a homework on that. And then at the very end on Friday, we'll have one final quiz, a very short quiz, probably about 10 questions, just to finalize the year. Again, I appreciate you listening. Thanks so much.